we are going to end this session this afternoon with a conference on smart sensors, which is the third technology field. And Patrick, who else than Patrick, to talk about, infrared sensors.
Can you hear me? Yes, it's okay. So I thought this talk was tomorrow, so I'm a little bit surprised, but I'll, I'll go ahead. Okay. So it's going to be about large volume infrared sensors. This is the sensors made based on the Microbolometer technology. So you've seen this slide earlier today, and you will see it again tomorrow. Just want to show you what we are talking about, and this way you will be able to compare from one technology to the other. So here we are talking about this type of technology where we have absorbing material that absorbs infrared, gets heated, and we have a thermometer material that changes properties with temperature. We measure the temperature difference by measuring the property of this material. It's basically a resistivity that changes with temperature, and this is transmitted to the readout integrated circuit, and that's the way we make an image. So this is the microbolometer technology, and the wavelength range is in the 10 micron here, 10 micron window. So a little bit of technology. I told you we have a thin membrane that heats up. That membrane has to be under vacuum so that it doesn't. There is no thermal loss. So it's a thin membrane with vacuum above and beneath. It's made on CMOS wafers, so it's a MEMS above IC design. And so we designed the rake, readout integrated circuit. We have wafers made by a foundry, ST for example. And then we do additional process on top of that, basically the MEMS process, to have what you see here, which is basically those very thin membranes with two corners contact to be able to measure the property of the material and detect the temperature change. And so end result is this type of product, the chip or the chip integrated in a module with the optics. So this is what was the international competition for this type of device 10 years ago. You see activities in the US, activities in Europe, some activity in Asia. Since then, 10 years later, this is the landmark. This is what the competition is today for this type of devices. So competition in the US and in Asia is really, really strong now, with a lot of new players in China especially. Not many more players in Europe, it's still the same, and some consolidation in the US. So there is very strong need to make our position stronger. And so IPCEI was also about this, about developing technology that will make the technology strong in Europe. So what are the large volume use of microbolometer sensors? Here you have two examples. You saw the first one on the right earlier today with for automotive application, where you can see clearly here with infrared people on the side of the street compared to visible image here. And this is another application for smart building. This time it's sensors with low resolution. It's basically 80 by 80 pixels. It's just enough to be able to identify people and count how many people are in a room. so that you can adjust air conditioning, light, and so on, and detect also if people are left alone in a building in the case of a problem. So this is large volume application for microbolometer sensors. And to be able to sell these markets, you need to reduce the cost, obviously, and also added values. And that goes through, in our case, pixel size reduction to be able to reduce the cost. And we are down now to 8.5 micron pixel pitch. We need to improve figure of merit beyond NETD. So if you had time to go to the website, you would know what NETD is. It's noise equivalent temperature difference. It's basically the smallest temperature difference that you can detect with the microbolometer, and that's the classical figure of merit of a microbolometer. But there is other parameters, and we are also working on these other parameters, not just this one. And you need also to integrate as close as possible to the detector some sort of signal processing to be for the product to be easy to use and more compact. And I'll show an example of this work we've done in IPCEI. So here, first, this is a movie we made with an 8.5 micron pixel pitch sensor. So that's new. I don't know how old is the movie. A few weeks, 1 month. Okay. So you see it's becoming real. Very small pitch sensors, high resolution images. I was talking about figure of merit other than NETD, and one figure of merit is the thermal time constant. Because the detection is thermal, you measure the temperature increase, it's slow. Basically, it's slow. Everything thermal is slow. And usually, with the usual microbolometer, you have a blurred image because the time constant is slow. So here, for example, a regular microbolometer sensor, you can't see much here. It's all blurred. We developed new technology that makes it possible to have shorter time constant and have sharp images with the new technology. Here, for example, I don't know if you see it from the room, but you can see spokes here. So that's one development also that we did with the IPCEI program. And finally, coming out of the readout integrated circuit, the microbolometer image is not really ready to be used. Here on the left, that's what you see out of the microbolometer. You need to do calibration and then signal processing to be able to really use the image. And that's what you have on the right. And we've developed algorithm and companion chips to be able to do that close to the sensor. And that's the reason why, you, for example, outside you can see a very small module able to produce good image. And another well, microbolometer sensors work at room temperature. There is no temperature control of the chip. So whenever the condition change, there is an impact on the quality of the image. So here you see a test. We've developed algorithm to be able to compensate for temperature change of the chip. And here, so we started at 17 degrees centigrade and went up to 25 without the shuttleless algorithm correction. The image on the right degrades a lot, whereas the other one stays good. So that's pure algorithm to be able to better control and have better quality image. And finally, I was talking about integration. We've developed modules with the chip, the focal plane array, the optics, the ISP, image signal processing chip, and we've combined everything to have small modules, easy to use by the customers, easy to integrate. And so that's what you see outside. And that's the demo you have in the lobby. It's the new product that was developed in IPCEI, the ATI 320. And so you will be able to see it again tomorrow if you want to have to see the image and discuss about it. Thank you. Any question?
Thank you very much for that nice presentation, and there will be plenty of time to have raise questions. Okay, let's have one question. Yes.
Is there any interest for you to work in the far infrared terahertz waves?
Terahertz, there is work being done on terahertz since quite some time. The thing is that the market is not really identified yet. It can be used for quality control, for example, for food, for cereals and so on, but it's still in the infancy, I would say. Technology is moving faster than the need for it right now.
So technology is ready?
I know that CA-Leyte, for example, is working on it.
Okay, thank you very much.